All right, back for part two, and here we go. Oh yeah, forgot. I'm going to go through this one quick because we have seen these before. We know just about all there is to know about instantaneous rate of change. At least we think so. And so I'm going to go through this one quick. We'll see a lot of review stuff, maybe things that we haven't thought of for quite some time. This one I'm taking from the textbook. It's a table that shows, and poorly scanned here for some reason, but a table that shows the population over time, and this is the population of the United States of America. And the question is here, how could I find the instantaneous rate of change in 1960? So this would be how fast the United States was growing in 1960. We can see it's growing, of course. Well, how would we do that? How we first did this way back when? Way back in Unit 0. Think back, way back, Unit 0 was, we kind of could do just the best that we have from the table, right? We'll try the centered style, right, which is just go from here to here, which, by the way, isn't very instantaneous, a 20-year change, but we get that it was going up by about 2.6 million people a year on average if we use a centered interval. Preceding interval would be from here to here, and we use the same calculation. And then the following interval, we get a slightly different calculation. So 3 different calculations. We can find the arithmetic average, just add them up and divide by 3 and say, yeah, maybe it's about 2.6 million people a year. And we did this technique in Unit 0. We also said another way that we might want to do this is by getting a model. I mean, it was easy when it was like that. If we could find out what the model for this function would be, for this table would be, we could just do it like the last example. And how do we do that is we can use technology. So one is in Desmos. So and I'm going to use TI-83 and Desmos real quick because I got everything all typed in, and I know I'm going to be going fast. You can pause and absorb as much of this as you like. So in Desmos, desmos.com, I added a table and put all the data in there. And notice I didn't put the dates. This is the number of years since 1900, right? And there's the data. And notice this is, I can't even see the plot. I'd have to change these values. X-axis would go from 0 to 0 to 1,000, and 0 to 100 rather, and the y-axis values go from, I don't know, maybe I'll go 50 to, what did it go, almost to 300, right? And we'll let it figure out what the step should be. And there, dandy, there's the scatter plot. How I do regression on Desmos is I type in this sort of thing. I'm going to go, I want a function of the form y1 is about equal to, and that's a tilde, a times b to the exponent, and then x1 was my table. Did you see when I put in the table when x1, y1? And there it plotted it, and there are my values. Okay, my a1 is 8.2 or 82.6, and my b1 is 1.01. It would have been nice if I got a couple more decimal places there. I wonder if I can get it from here. No, I can't. But that gives me a decent idea. So back on the back to the note, I've got, what's that? What is that? Back to the note. Okay, good. I've got, what is it? 82.6. B was 1.01 to the exponent x, where x is the number of years since 1900. And then I can take that and approach it in the same way that I did here, right? I just go, use my Iroc formula. Once I get a model, it's old news. That's too bad that we didn't have another decimal. So notice it looks like the population, according to this model, the population of the United States is going up by 1% a year. Okay. TI-83, I kind of like the TI-83 for this because it's got more tricks that I'm familiar with. I'm sure Desmos has tons of tricks, but what I did here, and I did this already, so I put all my data in. Notice, and I did something a little bit different, and this is just to show you that it still works no matter how you define it. I didn't put in 0, 10, 20, 30, 40. I put in 10 or 1, 2, 3, and this has been the number of decades since 1900, not the number of years, the number of decades. So I can come up with a slightly different model, but I have to keep, remembering what that means. That when I get an answer, that's in decades. X is in decades, not in years. And then I did my exponential regression. Right? Calc went down to exponential regression here. Exponential regression. Notice that if we needed a log regression for some reason, that we'd use 9 there. It says ln, which is different, but it is a log regression is 9. Exponential regression is 10, and then I do that, and then I went to y equals, and I didn't copy that in. I'm going to show you real quick how I copied the regression equation in there. I'll clear this out and do it again for you. So once I've done my regression, I go vars and then down to statistics, and then you see how it says equation, go over to equation, and then it'll copy it out there. And then if I've got my plot turned on, I can go zoom stat, zoom 9. Data management people, hopefully you're following this. We don't, by the way, functions folks, some of this should be familiar, but I know not many of you will have these steps memorized, that you'll have to work on it. And we'll talk about whether we'll be using these on the test. Not much, probably. Very small part of our course. So there's our regression function right there. And if I wanted to get the Iroc, certainly I could just use there, and notice 1 point. So why is this one so much more different than the Desmos one? Well, remember, this is 13% in a decade. Remember, my X was in decades, not in years. All right. Anyway, back to the Iroc. So I could use, I could use this and then do it like example 1, but I want to show you that that the good old graphing calculators have still got some tricks left in them. One thing I can do, remember, and we've seen this a few times, is I can, hang on, put that back to the graph, is I can draw a tangent on here. So second draw, I can draw a tangent 5, and I want to do it at x equals 6 because that represents 1960. And then it gives me the tangent, the equation of the tangent line there, and the slope of that tangent is 21.5. Right, and there's that. The Iroc is 21.5, and that's million people per decade, right? Because we had defined x going up by 1s instead of 10s, so that would be, 21.5 million people per decade would be 2.15 million a year, right? Million a year. And that's pretty close to what we had up here. A little bit different, but a third way. You want a third way? Why not? And this is kind of, maybe this is what your instinct would be. We know what we're pretty good at writing exponential functions. The initial value was 76. If I could find an a value, and I'll explain where I got my a value here in a second, is then I got my function, I could just proceed this way. Well, how much am I going up by? Well, I could calculate all of the rates of change. So this population divided by this population gave me a growth percentage of 1.21, which meant 21% from that decade, 15% in that decade, and in fact, I went ahead and did them, and I found all these rates. And so, how would I decide on what single rate to put in here? Well, you might be thinking, let's find the average. Well, the thing is if I found the arithmetic average, adding them up and dividing by the number of numbers, these numbers, these ratios, aren't found by adding and subtracting. The arithmetic mean is actually inappropriate here. But there is another type of mean that we can talk about for ratios, and it's called the geometric mean. Instead of adding up a bunch of numbers and dividing by the number of numbers, we multiply up the numbers and take the nth root. So there are 10 rates. I can multiply them all up, and then I take the 10th root, and I get 1.14. So that means, according to this model, with the geometric mean in there, the base is 1.14, and then that means it's a 14% increase. Again, this is per decade, right? Because from here to here is 10 years. That's per decade, increase per decade. And then if I wanted to, I could use the Iroc formula. Once I have my model, then this is the same old boring story where my x is 6 decades, 1966 decades, and I subtract them and I divide and I get, you know, very close to the same answer I got from the TI-83. Okay? All right, talk about an example overdone. Now, which way should you do? Well, I would try, because where's the homework? Oops. I would try a little bit of all of them. Okay, you're going to have a favorite style, and there's probably only one or two questions like this from the table, but try it each of the ways. Or in your groups, one person try it one way, one person try it another way, and a third person try it the third way, so you can sort of understand all of the different methods. All right? All right, well, that is it for the log chapter. Have fun with your homework. You, rate of change. Yes, you rock.